and get to see some interesting talks so far. I knew that since I'm going relatively towards the end, I don't have to introduce power amplifiers, which is always convenient. But what I wanted to focus on today is within the context of GaN MMIC PAs, how can we think of taking all these ideas that we've seen over the last hour or so, and also borrowing some ideas from what's currently done in the hybrid and sub-6 gigahertz world, and what works when we scale it to MMIC, what doesn't work, how can we especially focus on efficiency over backoff. So as I'm sure most in the audience are already aware, there's a very fundamental trade-off with a single transistor to get efficiency, linearity, bandwidth all out of one device. And if you're trying to use your device for communications and you have high peak to average power ratio signals, you are fighting constantly with this idea of getting both efficiency over power and efficiency over bandwidth. And so that's the context that I wanted to focus on for this masterclass today. As I mentioned, there are a lot of answers to these questions done already at sub-6 gigahertz and in hybrid and high power PAs. And so with that in mind, I want to talk a little bit about what is specific to GaN MMIC design, especially considering some of the, let's say, fun quirks of the MMIC or the GaN device that Professor Asbach already mentioned this morning. And then I want to show you some of our designs at some X-band and above for efficiency enhancement and different ways of addressing the bandwidth issue. So the first kind of piece of the seminar today is looking at the question of bandwidth. And like a lot of the other speakers, we think a bit about how do we model the devices. And in particular, in my group, we're not really interested or specialists, I guess, in large signal models. What I want to present as a sort of simple alternative is a method that we use and is used by other groups as well to do rapid simulation of broadband. I will caveat my use of the word broadband because I know that we'll hear about distributed amplifiers next. And in this talk, I'm focusing on reactive matching. So the concept of broadband is maybe up to an octave. And if you want to go beyond that, you're looking at distributed techniques, which again, Mike Broberg will talk about in the next presentation. So, okay, so I want to design a MMIC PA. I've picked my device technology, I've biased it, performed some kind of load pull, pick some load impedance, right? So this is sort of the very basic, very fundamental idea of how do we think about starting to design a PA. This is an example. This is just a commercially available, actually bare die device, and load pulled at a very relatively low frequency, 3 gigahertz. And this is fairly deep into compression, so we see a difference between the output power and PAE optima, and we pick some load impedance. So a common next step is that I would then try to design a really simple matching network. And of course, in a perfect world, that matching network looks something like this one that I'm showing here, where it has a shunt reactance, a shunt inductance specifically. That's a good way to sneak a bias T in. It has a DC blocking capacitor, so I can both match and bias at the same time. And if all things kind of are going smoothly, I can simply model my target load as the conjugate from the load impedance and design the matching network in that way. First of all, why would I want to do it this way with a port instead of using the large signal model? You'll see in a lot of our designs, we use a small signal approximation to the large signal model, which seems very roundabout, right? The load pull itself is clearly a large signal simulation, right? It's in compression. If this were a small signal, then our output power and PAE optima will be aligned. But at the same time, so we need the large signal model. Power amplifiers are nonlinear. Can't model it with S parameters. But at the same time, in the simulator, and especially MMIC design, we were relying a lot on EM simulation and optimizers. we want to also be able to use S-parameter simulations in order to speed up that process. And so this sort of thing is a very optimistic way to approach that, but of course it doesn't really work, right? So then you say, okay, I have this port impedance, I picked it from load pull. Now I try to operate at not just one frequency point, but some kind of bandwidth, and it starts to fall apart. We don't, we need the target, the load target to translate, to move along with the load pull impedance targets. And so now in this Smith chart at the bottom right, I'm showing the same device under load pull, peak power points in blue, peak efficiency points in red, but now sweeping from 1 to 3 gigahertz. So a very simplistic view will give us an overly optimistic match. And so you hear people talk about, like Bode-Fano and other matching constraints when we're looking at broad bandwidths, reasonable bandwidths, I should say. We always have to keep in mind that the target is also moving on us, right? The device itself has the intrinsic parasitics that make the match move counterclockwise in the Smith chart. So the simple way to better approximate this is to have a model that is, again, admittedly poor, but provides a good target for just in terms of matching network design, in terms of the passive network design, is to treat the transistor as a transconductance with an output capacitance. And that looks like a parallel RC. This is, again, not by any means like a new technique, and there's a very nice write-up on it from Chuck Campbell in the reference at the bottom here. But essentially, we modeled the device as an RC, and the R is the impedance of the current generator, and the C is the output capacitance of the component. So an example for this, again, same just nominal device that I've been showing on the previous slide is, in this case, maybe the strategy is to kind of split the difference between the output power and PAE optima. We want to target this black contour in here. This RC model now, which is for this device, it's very conveniently close to 50 ohms and about a puff of capacitance. This black contour now tracks the target, the load impedance target that we want to hit with the matching network. And if we are matching to that contour, then we've created a matching network that creates the correct impedance to present to the active device. So then I can take that model in the center, the schematic shown here at center, and try to match to that port 1. Here, the port impedance is the R, and then there's a shunt capacitance that is modeling that parallel C, the RPCP model. And again, if port 1 is matched, then this matching network design presents the desired load to the device. So then finally at the right here, I'm just showing a comparison of this parallel RC technique compared to a fixed, a constant impedance model. And you can see that indeed the impedance, the constant impedance model was overly optimistic. And the actual match to the device, which is, again, the target is moving, that's the problem, that's a problem. It's actually more narrowband than if you just used a fixed model. So I mentioned this is a little bit of just an aside, because as we're talking about actual efficiency enhancement techniques, we're going to move the model, like the target impedance is going to move over power, over supply voltage, also over frequency. And so when we talk about that, when you hear about like, there's a fundamental trade-off between efficiency and bandwidth, it's really due to a lot of these factors that we can simplistically model and try to account for these behaviors in the circuit design. And so that's going to be the focus of this work. How do we actually model this is also an important topic, right? So, okay, I have an RPCP model. How do I come up with this? There's a lot of different ways to do it. To be honest, you can, in some sense, just visualize the result based on load pull. But as was mentioned in previous talks, sometimes we don't want to load pull the device because it's intensive, either large signal simulation or measurement, and it's resource intensive to do so. So rather than performing a more traditional load pull, we can also use this simplified model for the device. It's really a model for the impedances that we want to present to the device, with a simulation setup that looks a little bit like load pull, but is more of a direct solution instead of a brute force, just load with every possible impedance and see what happens. So the schematic for that is shown here. This is an AWR example for, this is a PDK device for a GAN process. And we have here very simplified a bias T on the input and output. We set our bias point. We allow the optimizer, all of the red parameters shown in red are optimizable. And so we let the source impedance and the input power be optimized. And then we basically set up constraints that say, select a RC, parallel RC value that gives me a desired performance at my desired frequency. In the example I'm showing here on the right, we were doing a 28 gigahertz design where we were looking for certain input match. So you can see the optimizer goal here in this plot on the right, and we're looking for a certain minimum gain. In the simulation setup, we actually use a negative, so positive R models the power, like the load, the real power of the load. And then a negative capacitor is used to model the C. And again, this is because in the Smith chart, the transistor wants to see something that's moving in a counterclockwise or non-Foster rotation direction. So essentially, we're asking the simulator to tell us what negative capacitance exists to cancel the large signal capacitance of the device under the excitation that we will subject it to, so that all of the power delivered is real and that we simultaneously meet our input match and gain goals. In this example, just continuing the example here, we're comparing that model for that device that's shown on the previous slide to the actual, the kind of conventional load pull behaviors. And you can see that it does pretty much trend in the expected frequency range. So this is each of the call out and frequencies correspond to the load pull frequencies in pink and blue. Here, pink is a gain contour that meets our minimum gain requirement, and blue is a PAE contour. So you can see, of course, it's not going to align perfectly. This is over a 4 to 36 gigahertz frequency range. There are other parasitics in the device, but we're able to more or less capture the behavior of what the large signal operation is going to do. Then we can take this model and connect it to whatever load output match topology we're going to use, and design that match. And design, again, the whole idea here is that now this is a S parameter simulation. It's a linear simulation. It's fast. It's it's going to converge, all of those nice things. We eliminate all of the complexity of working with a large signal model. But of course, at the end of the day, just to be clear, you do have to go back and simulate with the transistor model. So this is a tool, but not a final solution. So the on the right here is shown, and we designed this match using this method. On the right here is shown a simulation with replacing this parallel RC model and putting in the large signal model. And we do see a good match over the band, maybe not as good as the ideal performance, but we do see that the band with the same matching network is well captured by the simpler model and using the same matching network topology. So this is some comments on this technique. It works. So this is a technique that we find works very well with MMIC design. Does not work so well with hybrid design because it does, of course, not capture any of the package parasitics. But if we are able to work at effectively like the actual drain of the device or very close to it, then you can use this as a starting point for understanding the behavior of your particular model. You can also refine things by, for example, requiring that limiting the Q of the match that you're willing to make because of your process or frequency or the combination of your process and frequency for MMIC. And then you can do a similar approach, by the way, on the input side, but of course the input to the device is best modeled as a series RC because of the physical structure of that. So as an example, PA designed over broad bandwidth, just with kind of reactive matching with a relatively high order matching network. This is a 150 nanometer GaN PA from 6 to 12 gigahertz. And in blue and red are the load pull simulations. In the blue circle, this is the constant conductance circle of like the RPCP model, so that you're moving around on the parallel resistance line, and then as frequency increases, the effective reactance moves you closer to short. This particular PA was characterized over the octave, sort of an extended X-band 6 to 12 gigahertz, and we're able to get quite good performance and have demonstrated with modulated measurements, and this sort of thing works, right? That's the conclusion of this part. So that's one technique, and then what I'd like to do is keep that in mind. So we're going to model this behavior of the device. But what's not shown here is any kind of efficiency enhancement, which is actually the major topic of this presentation. So how do we remember that the device is very unfriendly from a bandwidth perspective, that when we're thinking about reactive matching? And then we're going to add another degree of complexity to this by wanting efficiency enhancement over output power backoff. So let me briefly kind of forget MMICs for a moment and just talk about very basic, very optimistic, I should say, concepts here. And then we'll talk about practicalities again, with the idea of, well, okay, this sounds great. It was invented for AM radio. How do we take some of these ideas and put it into a GaN MMIC? So the efficiency and output backoff solution that is most used today is the Doherty amplifier, right? And that uses load modulation, where effectively we're saying that if we want to reduce the output power of the PA, we will change the load line dynamically. And this will, in theory, give us perfect efficiency flatness over power. In practice, our devices have knee voltages and on resistance, and we see something more realistically that degrades with output power, but less quickly compared to a Class B, for example, PA. As Professor Asbeck mentioned this morning, and it doesn't actually look like this. The GaN PAs, one of their challenges is that the target load impedances are not great. So I want to talk about that. But essentially, when we think about load line manipulation in GaN PA, what we're really doing is, instead of looking at the output peak power contours and the peak PAE over frequency and kind of picking an in-between route, we're trying to dynamically move so that at peak power, we're at the peak power point, and at back off, we're at the peak efficiency point. So we're doing a dynamic load variation and ideally working in the frequency response as well. So the technique that I wanted to cover today was outphasing, which is not as popular in hybrids of 6, but in GaN MMICs is somewhat appealing because the transistors are always on. And so we have less of a potential for gain degradation into deep off. And so my group has been exploring, how translatable are these concepts to X-band and K-band power amplifiers. The big picture concept of outphasing is that you have two voltage sources driving a differential load. And as you change the relative phase of the two drives, you get different effective impedances seen into the two PAs. So if you drive the two equally but out of phase, you get the maximum current through the resistor, which gives a small effective resistance. If you drive them the same on either side, then you get effectively an open circuit between the two nodes. And any kind of combination in between can give you an impedance between this R/2 and infinite load impedance. On the Smith chart, this the load trajectories look like the ones in black, which actually are not great for most power amplifiers. And so what Henri Chirex developed when he came up with this idea in the 1930s was to introduce compensating impedances to shift the upper trajectory down and the lower trajectory up, so that we get a load modulation of both PAs that to some extent hugs the real axis of the Smith chart. And you can choose here to trade off more dynamic range and resistance, which comes with more imaginary part to your load, or you can move the lines closer together and get a smaller dynamic range, but a broader, but more resistive loading overall. So with the idea of mimics in mind, I want to talk a little bit about different ways to implement that floating load. So if you just break down what an outphasing combiner does, it's really performing two functions. One is there's a floating load that is in practice going to be single-ended. So you have to do a single-ended floating conversion. And then the second piece is this compensation reactance, this idea of moving the two curves closer or further relative to each other. So the kind of original outphasing was like transformers and shunt reactances. We don't see this so much now in hybrid PAs, but actually my group has done a version of this in MMIC, because once you get up to 30 gigahertz, you can do like an edge coupled transformer, and this kind of technique becomes attractive again. You can also do a reactance, lumped series reactance, it turns out, can give you the same effective behavior, as can an all transmission line version, where you're actually using, these are effectively like usually 90-degree lines plus or minus some length, and that plus or minus delta length performs an equivalent function to the plus or minus L and C. So in the Smith charts here, I'm showing what happens with each of these techniques as you shift the frequency away slightly from nominal. And you can see that they all look the same in band, but then as you shift the frequency, because of the different structures of the combiners, you get different frequency responses. How do you pick which one to do mimic? Well, I mentioned we did a version with transformer at Ka band. The PA I want to tell you about first is a X-band mimic, and we actually ended up using this quarter wave line structure. We considered the lumped element structure, and I have seen some work that does that. But when you're working in a mimic, as many probably know in the audience, your tolerance of your lumped elements can be pretty bad, right? So like plus minus 20% accuracy on that inductor capacitor, and also, especially with the inductor, you can run into self-resonance issues. And so we were able to, so what we did a little study and compared these two techniques on the right. The LC series works best in terms of loss if the values are correct, but was more sensitive to tolerance issues compared to the lines. So we ended up, as you can see here in the mimic photograph, using very long for X-band transmission lines. And even though there was a higher penalty to insertion loss, we were able to get a wider bandwidth behavior because we weren't relying on hitting L and C, just precisely, which we know we can't do in a typical mimic process. So this is a 150 nanometer GaN PA from 8 to 11 gigahertz. About the frequency response is shown here. This is just simulation. And then at the bottom is measurement at 10 gigahertz, where we're sweeping the phase, the relative phase of the two drives. And then each of the curves is at a different input power level. So the two powers are the same, but not constant over the desired output power. More on that in a moment. And then what you see in the dashed line is the kind of just regular drive out, just sweep input power. And what we see is that we get so up to about 10 points of efficiency improvement at back off by doing load modulation instead of classical. Although I will comment that this is a simulated result, so that we don't have a direct measurement comparison So outphasing, I guess I will say, does seem to work at X-band, but there's a really important consideration that we need to account for, which is how do you actually drive this thing? And what the theory tells you, like when you read the outphasing papers, right, we talk about this constant input voltage and we do phase control. And that's actually a really ineffective way to drive a power amplifier. The behavior that you get out is sketched here on the top right. If you keep the input power to an amplifier constant and you change its output power, then your gain goes down, right? Your gain, if you keep Pn fixed, you will rapidly run out of gain as you start to back off. And that's what you observe, right? So here, in this plot, we take this MMIC PA and do phase control. So sweep the output phase, sort of fix input power, and we get this characteristic. What you actually want to do with this system, and now here, this is not the MMIC PA, this is another example where I have the full set of data to share. But we're showing it over a number of different input power levels and over phase sweep. So each line here, each contour is a fixed input power. The two PAs are driven with the same power, and then the relative phase is swept. And so what you can see is that if you also reduce the input power as you back off, then you're able to maintain a flat gain characteristic. And actually, this is when you see it, when people talk about like a voltage mode outphasing PA, it's this manipulation of the input drive that enforces that constant voltage, because you're changing the load condition, you also need to change the input drive. So this leads to something called the signal component separator, which is this very nonlinear function that takes the desired input signal and gives us an amplitude. So x-axis here is the desired output power. And then we have a particular input amplitude we want to drive the two PAs with, as well as this outphasing angle, which is the dashed line here. So this is where outphasing has a bit of a drawback from conventional, like from Doherty, which is that the input drive is hard to do. I think I'll go quickly through this because I know we're a little bit behind schedule. But essentially in my group, what we have done is said, let's not try to do that with digital signal separation, because as you scale to higher and higher carrier frequencies, your fractional bandwidth comes along for the ride. Outphasing, you get 10% bandwidth easily, but the instantaneous bandwidth, doesn't necessarily scale as easily. It may be very challenging to create something with 3 gigahertz instantaneous bandwidth if you're doing it in the digital domain. If you're doing it in the circuit domain, it's actually a little bit easier because your whole system is scaling, and fractional bandwidth is the kind of constant that sticks with you as you change these frequencies. And so we developed a technique to create those input signals in the circuit domain. There's a paper on it that I'm citing here, but essentially we apply the concept of time reversal duality to the combiner. I say, what if we flip the combiner around backwards, and we load it with something? If we load it with a nonlinear resistor that changes with the function of power, then that same phase will appear at the output of this in-phasing network that I needed for the same resistances at the out-phasing network. I realize that was very quick, but essentially I have an input, a nonlinear resistor changing as a function of input. That creates a power-dependent phase, which creates a phase-dependent output voltage. And when you put it all together, you actually recreate that input signal split. I see a question about the digital splitting and outphasing versus Doherty. In terms of bandwidth expansion, I think they are comparable. The complexity is arguably slightly higher for outphasing because you're doing both phase and amplitude, but in practice in Doherty, you also need to account for AM, PM in your device. And so it's very, I would say, analogous in the sense that if you try to do dual drive NEPA, you're going to get a 5 to 7x bandwidth expansion that will really can inhibit the instantaneous bandwidth that you're able to drive through your device. Since we're talking about GaN mimics, we looked for a nonlinear resistor for this in-phasing strategy that is compatible with MMIC technology. Right? The end goal is to put this all in one chip. And so a former student of mine, Daniel Martin, he compared pin diode, MESA resistor, which I guess Mike Roberg's on the call, so thanks, Mike, for pointing out to us that the MESA resistor in GaN is very nonlinear. We actually use this for nonlinear resistance and in-phasing, or like a diode-connected transistor, which of course is also going to give you ultimately a nonlinear resistance. So we took these nonlinear elements and compared them in different networks to get this outphasing response. And what we were able to essentially what we found is that the MESA resistor gave us a nonlinearity that was best suited for the nonlinearity of our MMIC PA. And so when we put those two pieces together, we were able to do an RF input outphasing. So now it's single input, single output system that was, again, this is a 10 gigahertz measurement here on the top right. It was about 9.5 to 10.5 RF bandwidth. And we're able to get RF input outphasing performance that was comparable to our dual drive, but with much kind of easier to operation, much lower complexity. And that also allowed us, for example, to put modulated signals through it without needing to do anything heroic in terms of input signal generation. I actually just threw in the slide while I was attending other talks this morning, because this particular PA, we took the approach of, we had a device with a matching network and then this combining structure. You can also go directly from load pull to outphasing, right? The combiner can also fundamentally just move you from the P out to the PAE point. There's some great work out of Christian Fogger's group at Chalmers University with the black box technique, looking at this. And then this PA that I'm showing is from a PhD student, my colleague, Professor Popovich's group, where they did an X-band outphasing structure that was sort of tuned up to just match the load impedances for a PA. And I wanted to highlight this because indeed you can see that the load contours are not great for this GaN PA. This is another X-band design. And then if you really care about efficiency at backoff, you may look at this and think maybe we should also add supply modulation. I know that works at sub-6. Does that work in MMICs? Short answer is yes, it also works for GaN MMIC design. And so this is that 6 to 12 gigahertz PA I mentioned at the start. Characterized, this one was actually designed for load modulation, so it goes down to 16 volts from the nominal 26, and you see an improvement in backoff. And then we actually took the PA from the previous slide, the outphasing PA, and added supply modulation to it, so we can combine these techniques with each other and get outphasing curves that are also benefiting from supply modulation. And that really builds in a lot of efficiency into backoff. So in this example, this is like a 4-watt PA, but then at 1 watt out, we're still at something like 45% efficiency, and that includes the supply modulation. Bandwidth is, of course, a major consideration, and we'll wrap up here, but essentially, I mentioned that we could do transformer coupled, like transformer structures if you go up high enough in frequency. So we have a PA that used a transformer with shunt reactive elements, and the reactive elements are implemented with transmission lines with pin diodes that let us select the effective length of the line by grounding at different points. And this allowed us to track that RPCP model, that parallel RC in frequency, and get the load variation. This one was a gas MMIC, 20 gigahertz. Actually, I should say 16 to 38 gigahertz, 28 is the center. We're able to frequency reconfigure over that whole band and get efficiency enhancement and backoff. So again, you can combine a lot of these ideas and get systems that are increasingly complex, but by doing some of the signal processing and analog, we're able to try to mitigate the complexity issues. So that's where I'll leave off, but we are kind of looking at understanding basically really almost overly simple models, but how does that let us to think about circuit design and from an architectural level of addressing certain behaviors in the PA? We care about bandwidth, but we care about RF bandwidth and instantaneous bandwidth. And so we do have to worry about both simultaneously. And then we've looked at combining various different efficiency enhancement techniques of frequencies from about 10 to 50 gigahertz, and see these benefits, although it may be diminishing returns compared to some of the more ideal stuff at sub-6. So I wanted to just acknowledge the students worked on the group, one of whom is the designers is our session chair, Prasmesh, and also Daniel Martin, both of them graduates of the group. And I'd like to acknowledge MIN Semiconductors for fabricating some of the MMICs. So I'm happy to answer questions.